That will be due when you come to lab next week. I'm still working on the unknown lab reports. Any other questions or things to take care of before we get going? Good to go, Samuel? And next week we're doing bromination of an alkene, transphylbene. Okay, which we should cover today, get to. Where did we leave off at? Ring expansions, yeah? Did we do the mechanism for this one at the top? We got the remember name. Alkene is the reactive site here. Pi electrons, reactive, held loosely, they can react with H+. B or minus, we can just show this ionically. Where would we leave cation, top or bottom? Bottom, these electrons, okay, it's like a hinge or a door. Swing out, all right? All right, if you want to open that door, you pull it from the side that opens. All right, just pull it here. The arrow needs to mean something. These electrons swing out and make bond to H. This is going to give... By the way, I have no idea what the full mechanism is. But I know the first step, mainly because that's the only first step we've ever done. All right? I don't have to worry about, I don't have to know the entire mechanism when I start. I start one at a time. All right? What else can I do here? Nothing. Alkanes don't react with HBr, only the alkene pi bond. And that's going to give UH here, carbocation here. Okay? Now what? Well, some things you have to just kind of know that as possibilities, and we're showing that ring expansion is a possibility. We went from 4 to 5. I mean, if Br minus attacks here, you don't get that product. So we can't just do that. That is not the mechanism for giving that product. We can do rearrangement though. Carbocations are always prone to rearranging. Today, organic 2, whenever. They're always prone to rearranging. 4-membered ring has some ring strain. 90-degree bond angle from 9th grade geometry. 5 and 6-membered rings are better. This methyl could shift over here. We could take this here and disconnect here and move it over. All right? That would give boom, boom, boom. We can. Okay, you guys have got to see backbones. It seems like typical, if I draw the backbone any little way differently, you guys typically almost freak out about it. Don't. It's the same thing. Differences. I didn't draw the H in over there, but it's there. The new H is over there somewhere. You got to know where it is. Also, I mean, why didn't I draw this methyl up and that one up or whatnot? Well, bond angles. I mean, what do you have? You got a carbon. That's a CH3. It's a CH2H draw. That's a CH3, which is a methyl. I'm moving a methyl over, so it's a carbon with 2 methyls. It's a carbon with 2 methyls. It's all there. Okay? But that right there holds a lot of you guys up. I don't know what just happened. Well, look at the structure and I'm sure you see what's happening. Okay, does this get us closer to product? Again, Br minus could attack here, but that ain't that product. And if you think about it further, we're not going to get there from there. That is, let's turn around. Let's don't go down that road. Let's turn around. Really, we need to see here that we need to do a ring expansion. Instead of moving this bond over, what if we move this bond over? So don't do that. Here's this bond. Take it and move it over there. These electrons and move them over here. What does that do? All right, I'm going to redraw this sort of exactly like I got here. And then I'm going to erase. I'll draw in the H. I'll draw it exactly the same. Isn't that exactly the same? Just bigger? What do we do? Here we go. We move this over here. So I disconnected it from here. There's the atom. These are the two electrons. The two electrons, instead of making bond to that carbon, are now making bond to which carbon? That one. And the plus is no longer here. Where's the plus? The carbon that lost the bond, here. So that's what this electron movement gives. Right? All we did was just do this. But look at this now. It's a little bit ugly, but what size ring is this now here? 1, 2, 3, 4, 5. Yes, let's draw a nicer 5-membered ring. And it's got a carbon that's a cation, and that has a methyl. You can do it anywhere you want. Carbon with a cation and a methyl. So it's like this, yeah? Methyl and that carbon's a cation. Next door is another methyl. That's a CH3. I just drew one H in. So next door there's another methyl. So this is that. Well, at this point, can we get home from here? Well, if you look at it, all we got to do is now, this Br minus has been watching this. These electrons add here, and what do you get? You get final product. This is a carbocation rearrangement. Essentially, this bond moved over. But because that bond is part of a ring, it changed the ring size. And this size, it went to a larger ring, and we call that a ring expansion. Could this pathway have happened? Perhaps. But this is a mechanism question. I'm showing you a product, and I'm asking you to draw a mechanism. Is this a major product? Perhaps. But guess what? I could show you a minor product, something that's formed in 2% yield, and still ask you for a mechanism for that. Anything that's formed has got to have a mechanism. Now, is this the major product if you were asked to predict a product? First off, cation top or bottom, here. What do we say about rearranging? Always rearrange, if you can, to a better cation, and that's going to be the major pathway. Did we go to a better cation?
Yes.
We went from secondary to what? Tertiary. But there's another reason it's better. What's the other reason?
Ring size. Ring size.
We went from a 4 to a 5. Yes, ring size. And we know 5 and 6 member rings are best because they have the best bond angles. Bond angles that have lower energy. So there's two reasons why we want to do this. What if we did a methyl shift here instead? Does that give a better cation? It is tertiary, but it's still a 4-membered ring. So this is the better pathway. Yeah? Ring expansion. Below is another example, but this looks like a ring contraction. 7 going to 6. It's also a hydration with aqueous acid, where above was a hydrohalogenation. Both of these have skeletal rearrangements via carbocation rearrangements. You can try this one down here on your own. and I'll supply a key at some point. Questions about the top one? Also, let me point out back to the green sheet, a couple mechanisms. The top one is very introductory, very basic. The one below is a bit more challenging, but it should still be straightforward if you know how to use mechanism arrows. I think this is very much worth spending some time on, showing mechanism for this. Good practice for your arrow movement. And seeing that every formation of every one of these things over here can be shown with simple arrow movement and seeing the electrons just moving. Okay? And I will also send out a key to this. I believe this and the expansion is on the same page. While we have the key, where are we at? Roman numeral. I think we just did carbocation rearrangements. Roman numeral 4. Ring-forming reactions. Roman numeral 5. Okay. Let's see about that. Now, the reactions we just looked at, we had a ring and it changed size. How might you form rings? Well, rings are typically formed when things react internally. One end reacts with another or something like that. An internal reaction is called an intramolecular reaction. Intramolecular. Where if it's two different molecules, that would be called an intermolecular reaction. Like an interstate goes between two different states. Let's look at this. Can we propose a mechanism here? If you take this is called a diene. Two enes, diene. If it had 3 alkenes, you would call it a triene. What if it had 18 double bonds? Or 11, or we usually just say polyene. Lots of enes, polyene. Okay? Have you heard of amphotericin? No? Y'all need to get out more. How we doing with THC? How was that mechanism? Enjoyed that one? All right, let's look at this. This diene here reacts with HI. Looks like a 6-member ring, yeah? Is that 6? I think it's 6, yeah. How do we do this? Well, again, the only reaction we know so far is reaction of an alkene with H+. We got an alkene, we got H+, so it seems like we know what to do first. The question is, where are we going to make cation? Right or left? Uh-oh, we got 2 alkenes. What do? We just have, instead of 2 choices, we got 4 choices. Where are you going to make carbocation? 1, 2, 3, or 4?
3.
Right here, tertiary. Hopefully we will be rewarded by recognizing that, and we will be going down a pathway that leads us to that. Let's see, H+. These electrons break away from this carbon and swing out here. That's going to give boom, 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 boom. Boom. Okay, and an H there, right? Everybody good? Everybody good? Who's not good? Thank you. Why not?
Because that's supposed to be a carbon, the H is supposed to be.
Yes, that's supposed to be carbon. then an H. Right? Very common mistake. Gotta keep track of your backbone here, right? As I had it, I mean, this has got 1, 2, 3, 4, 5, 6, 7, 8 carbons. The way I had it, it only had 7 carbons. We don't lose a carbon when something reacts with H+. Okay, don't do that. Where's cation at? Right here, right? No, it ain't right there. All right? Don't make these mistakes. The cation is here. Okay, what can we do next? I- could attack here, but that don't give that product.
Does the other end of the alkene react with H+?
Yes. We still have an alkene here. Can an alkene attack a cation? Yes, right here, an alkene attack a cation. Does it only have to be an H cation, or can it be some other cation? It can be a plus is a plus is a plus in most cases. We just have only seen H+. We've only seen an alkene attack H+. Can an alkene attack a C+? Yes. Can that reach over here? None is drawn, but these bonds are sigma bonds. You have free rotation, okay? All right? Can I slap my hand with this hand? No, it's way over here. But guess what? My shoulder has rotation, my elbow has rotation, and now I can do this. All right? You can turn this. I'm just going to redraw it. How about this? I got a carbon with 2 methyls up there. Let's see here. Carbon with 2 methyls. See, that's a methyl there. I'm not going to draw in the H. It's there. Here. From there, I got CH2, 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 then full alkene. CH2, 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 then full alkene. All right, how if I draw that like that? I could have even drawn this a little bit up here closer, but right here, these electrons, by the way, if we react this alkene, where are we going to leave cation, left or right? Right, we're going to break away from there. This all is going to fall into place. Break away and zoop, go up there and make the bond. Oop. What does that give? It gives this. Here's what you guys typically don't know. If you look at this fresh, which carbon here is making a bond to that carbon? A or B? Which carbon is making a bond to the top carbocation? A. A. But then what you're thinking is, well, why is the arrow coming from B? We're pulling them from B. Arrows don't show movement of atoms. We're pulling the electrons from B. Okay, this is swinging up like this. All right? This is still bonded there. That carbon is now bonded to this carbon. That's a cation. Which bond did we just make? We just made that bond right there. We can highlight it with a squiggly line. Where's the cation at, though, now? On A or B?
B.
Yes, the cation is there on B. Because this is B here. How many H's on B? Only one. Only one. Only one. There's only one H here. That's why it's a cation. You lost the bond. Okay, what is this? Can we get home from there now?
Yes.
Yes. I minus, been watching all this. These electrons, bam, right there. Make bond. Lone pair makes bond, you got 3 lone pairs left, and we're done. We have a intramolecular attack of the carbocation by the alkene to make a ring. Which is going to be faster? I minus could have attacked here theoretically. Again, it wouldn't give that product. Which is going to be faster? Which can attack this cation faster? The alkene or the I minus? Who can slap my hand faster right there? Me or Samuel? Hold yours up. Okay, when I say start, let's go. Start. You didn't even move, and I'd already clapped my hand. Because this is internal. Internal's always faster. It's easier. I mean, I didn't have a chance to attack it. It did. Now this sits here, and I minus attacks it. We can get a final product. What have we done? We've added HI to that molecule. The formula of this now has HI added. It's not a direct addition across a pi bond. It's got some other stuff going on. Okay, so there's an alkene attacking a C plus instead of just only H plus. Yes. Very reasonable, yeah? Okay, we made a ring there. Alkenes attacking pluses. Let's talk very generically. This mechanism shows an alkene attacking pluses, H plus or C plus. It also shows a nucleophile attacking a plus. Very common things. The THC mechanism is another type of ring-forming reaction. We just did this first one here, alkene attacking cation. What about some other type of nucleophile attacking the cation within the same molecule? That's the THC example. Okay? Please take a look at that. And propose a mechanism there. What's next here? Polymerization of alkenes. What type of polymerization are we going to look at? Cationic polymerization, yes. Is this worth noting and understanding? I think so, if it's a heading here on one of my handouts. Perhaps there'll be other types of polymerizations as we go along. Okay, let's look at this reaction. If you take this, how is it on nomenclature? What's the name of that compound? Name? Propane, do we need a number with that? No. Is it stereogenic? Okay, these are all basic questions that come from the nomenclature handout and video. All right. If we take propane here, react with an H plus catalyst, we can get a polymer. Polymers can be shown like this down here. Typically, a repeating unit showed in brackets or parentheses, and this repeating unit just repeats some type of number, like 100 gazillion. Repeat, 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 repeat. And these huge polymeric molecules can have very interesting physical properties. And the polymer field is a huge field. Lots of practical applications. Ranging from something as simple as like styrofoam cup polymer to larger things like plastics and bulletproof vests and all types of applications. Huge, huge field. How do you make polymers? You make polymers from monomers, and you polymerize a monomer. Alkenes are commonly polymerized. What do we call this again? Propene. If you polymerize propene, what do you get? Polypropene. Who said that? Yeah. Polypropene. If you polymerize vinyl chloride, what do you get? Polyvinyl chloride, PVC. Yes. All right. So there's a little free nomenclature too. All right. What if you polymerize styrene? Polystyrene, yes. We call it styrofoam. Slang name. Okay, because it kind of, you can blow air through it and it can kind of come up and it's real, density is real low and it's. Okay, how can you polymerize propane here? Alkene and H+. Have we ever reacted in alkene with H+? Where are you going to make cation, left or right? Here we go, swing it right here, and we're going to get boom, boom, boom. There you go, nothing new. Cation there. What can attack the cation? I'm showing a very generic H+ here. It's got to be a minus. We'll talk about what minus might be there. But we don't want a minus to attack. What do we want to attack this cation? The same thing. We want the alkene to attack again. Can an alkene attack a carbocation?
Yes.
Yes, the example above we did it, but it was internal. It was intramolecular. Here it's going to be intermolecular, two different molecules reacting. All right? Now, I wish I could just do that, but then it's going to look like a reactor twice. How about if I draw it down here? Give us some variety anyway. This can attack here. Okay, when we attack, where are we going to leave cation for this guy, left or right? Left. So we want to pull away from here and go attack here. We got to keep track of all this. I wish I had turned this the other way, because I feel like it needs to be, but we're going to go this way anyway. I'm not going to draw it clean. I'm going to draw it as if I'm working here and I've got to just deal with it. Let's see. Boom. 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 Bond angles are going to be ugly. Maybe we can do this and then redraw it and clean it up. All right? We just made, let's label this here as A, B, and C. So we can keep track of it. Which carbon just bonded to the cation? C. C. The cation was here. If I come down here, and that's 3, it's going to be CBA, right? CBA. We just made that bond here. We should have a cation though now, right? This came up here. Where's the cation at?
B.
B. we go. Let's just clean it up at the end. This is a very bad bond angle here. Okay. Typically, whenever you draw 4 bonds, you're going to have, if you draw yourself a line here, you're going to have 2 bonds below and 2 bonds above. I've got 3 below. No, that doesn't really work because, like I say, I've got 2 below here. Trust me, it's ugly. That's okay. What can attack this cation? Yeah, at this point we might can sort of get it working a little bit cleaner, like this. All right, this is going to attack A, B, C, D, E, F. Which carbon is going to bond to B? D carbon, yes. These electrons break away from E and go bond here. What does this give? I'll keep this freakishly ugly molecule going here. Boom, boom, boom. Boom. No, that's more straight down over there. Boom, boom. This is B. And now we have this bonded to carbon. Which carbon is it bonded to? E, B. D, E, F. D, E, F. We just made a bond D to B, leaving which carbon as a cation? E. E. Okay, what can attack this carbocation? Do we need to keep going? We'll do it one more time. A, B, C, D, E, F, what? G, H, I, is that right? Attack here, and we're going to get, I don't think I can draw that. I'm not going to draw it anymore. It's going to be the same thing. Let's see what we have here. Just keep going for another gazillion times. Okay, what do we have here? We had this initial H that came in. I kept it drawn in for a purpose. But after the initial H, we have a repeating unit. It's a CH2 carbon methyl. CH2 carbon methyl. CH2 carbon methyl. And you could keep going 1,000,000 times and it will just be CH2 carbon methyl for 1,000,000 times. So why don't we, instead of drawing it out 1,000,000 times, let's just kind of say, you know what, guys? We've got this repeating unit sort of here. Now, that's an ugly bond angle, so I can't really draw this here, but it's just CH2 carbon methyl repeating over and over. Let's just show it like this and say some type of number there, which means it's a gazillion, or maybe it's 100,029. We don't know, but it's just done this way. And that's what I got shown here. Right? I kept going some here, but it's there, cleaner. That's how we show polymers. We show the repeating unit like that. Does that make sense? Original H. What started this polymerization here? What did we use to polymerize it? H plus? Is H plus a cation, an anion, or what? It's a cation. That's why it's called a cationic polymerization, because we initiated it with a cation. You can also do polymerizations with anions. But that's going to be called a what? Anionic polymerization. You can also do radical mechanisms, and that's going to be called a radical polymerization. But this is a cationic because we used H+. By the way, what type of H+ would you use? If you go to the stock room and say, give me some H+, they're going to look at you like, well, what do you really want? Can't just give you H plus. What acid would you suggest using here?
Hydrogen.
HF? Okay, why HF?
Because fluorine wouldn't attack.
Because we know F minus doesn't do anything in this class, and it wouldn't attack the cation. We don't want anything to attack the cation other than the alkene. So you don't want like a, you would never use HBr to do this because Br minus is likely to attack this, and you're not going to get polymerization, you would just get a hydrohalogenation. You would use the same type of catalyst that you use for hydration, sulfuric, HF. Okay? Choice of catalyst, not HBr. Because Br minus is a good nucleophile. Questions about that? See your textbook about that discussion, and you can have an entire course about polymers. You ever heard of lucite? Type of plastic? Comes with metal and wood. You ever been to a new football stadium or baseball stadium, sat on a big, nice, thick plastic seat? Might have been made out of lucite or something. That's just a brand name for polycarbonate type polymer or something, THC. Okay, next on the, where are we at on the outline? I think we kind of ended Roman numeral or something up there. Where we're under A? We finished up A? Ready for B. These are going to be additional reactions without a carbocation intermediate. Okay? Also on this page here that shows a variety of reactions, we covered those at the top. Now we're ready to look at these below. And it looks like a lot of them. It is a variety of them. We've got to look for consistencies. The main thing here is dealing with each individual reagent. But each reagent has consistencies which are applicable to everything. It becomes just like math. You learn how to do multiplication and then you can do anything. Right? You're not afraid of 58 times 72. Or 58 times 75, or any of those, right? It's all the same. Because you know the core consistent way to do it. Yes, there's a little bit of memorization about what each reagent is and what, a peroxy acid gives an epoxide. Yeah, you kind of need to know that on your note card and stuff. All right, the first reaction we're going to be looking at, we'll start here at 1 o'clock and we'll work our way around, is a reaction with elemental halogen, X2. This is going to give a trans dihalide. This occurs by an anti or a trans addition, either way you want to say it, of the halogen to the alkene. The halogen is typically either chlorine or bromine. Those are the most common. Next week we'll be doing BR2. Elemental halogen, it's called. Okay, look at this reaction with chlorine. Okay, chlorine is not ionic. HCl can be shown ionic. Chlorine never ionic. Always covalent. Okay, HCl, we could show that. The very first time we showed it, we attacked and we kicked this off. It's polar. Partial plus, partial minus. Electrophilic. Electrons are going to be attracted to the H. Either there or again, or we can show it like this. It's Cl2 polar. No, it's not. Not formally polar. Not officially polar. But the halogens are schizophrenic. All right? They're very polarizable. Just about any molecule is polarizable. Non-polar molecules are polarizable. Hexane. We talk about IMFs of hexane. What is the IMF of alkene? Van der Waals? How do you get van der Waals? Polarization of the alkane through rubbing up against each other. Weak polarization. Okay? And once that happens, then you get that little stickiness IMF we call, all right? Well, the halogens are very polarizable, bumping into each other. Oxygen. Is oxygen around? Yes. Bumping into oxygen. Okay? This is something polarizable. Alkenes are polarizable. So it looks like it's not polar, and when I do something like this, it's like, well, it's not. No, it's not permanently polar, but it's temporarily polarizable character. All right? You got to understand that. Okay, chlorines. They're back and forth. I'm pulling on you, you're pulling on me. Oh, oxygen bumped into me, all this, and boom, I'm pulling. Ooh, right now you're partial plus because I'm pulling. Why am I pulling? Because maybe I'm connected to it. All right? And at that point, the alkene can attack. Where are we going to leave cation, left or right? Left. So this attacks, we get this intermediate here. Cation here. What are we doing here? One of the easiest reactions we'll ever do. Chlorine adds across the pi bond. 2 chlorines, 1 on each carbon. Which one gets the chlorine? You don't put 1 on each, that's it. You don't have to decide. 1 chlorine on each carbon and you're done. When we reacted here, we had to decide where the chlorine was going to end up because there was only 1 chlorine. 1 chlorine on each carbon and you're done. But what's the mechanism? High electrons attack the polarizable chlorine. We make this bond here, yeah? Cation here. Now, how can we get product? The other chlorine, how does it form? Well, what does that second arrow mean to you up there? Electrons moving on to chlorine to give it the 4th lone pair, right? That's how it formed. This could attack here, and if it did, it'd be your product. I know some of you are freaking out about this. I say freaking out, that sounds bad. You're concerned about this. I get the question all the time. The chlorine attacked from the top. Why are you showing it drawn bond down? That's because stereochemistry doesn't matter here. We'll learn when stereochemistry matters. Do you agree that I'm showing chlorine bonding to that carbon? Yes. The chlorine is bonding to that carbon. That's all we need to do here. All right? And A would give that product. Everybody agree? Problem is, A is not the mechanism. We know that for a number of reasons. And here's one reason. Which is going to be faster to attack this cation? The lone pair from that chlorine or this chlorine? Euchlorine or mechlorine? Who's going to attack it faster? Right here. This is faster. That's not an anion, but it's still a lone pair and it still can attack. No. This attacks. And what does that give? It gives this. Because this made a bond here. And this is actually a 3-membered ring. But that arrow does give that, right? That's what we just did. This is known intermediate called a chloronium ion. That sounds like a positive chlorine. Indeed it is. The chlorine is positive there. To charge. And actually the chloronium ion is the first intermediate here. This carbocation, what are we under on the green sheet? B? What does it say about B reactions? Do these involve a carbocation? No. Then why am I showing one? That's because that's just me. There's no carbocation formed here. What's going on here? The first two steps are concerted. As soon as the pi bond attacks the chlorine, the other chlorine is coming in. By the way, I call this back bonding. Okay? I call it back bonding. Hopefully that's sort of intuitive. It's kind of, the book is not going to call it back bonding. The attack of the chlorine and the back bonding happen at the same exact time. And this is not actually formed. And I say NAF. Not actually formed. Most books will not even show this. We'll pull it down. I'll redraw it up here. Most books will show this like this. These electrons attack chlorine. These get pushed off. And at the same time, these electrons come here. These three arrows I have over here. I have it though as two, then I come in with the third arrow.
Is that okay to do?
This is okay because it's strictly correct. Yes, it's okay. Why do I not do this? Because I think you guys have terrible trouble of seeing what's all going on here. And the fact that cation being here is going to help us down the road. As long as we remember that this is just Stevens on the board doing this and helping you to understand it, and trust me, because I don't think this works and you're just going to end up trying to memorize it. Okay? All you got to do here is just know that these two happen at the same time. All right? Chlorine. You guys are chlorine. I'm going to pi bond. I attack you. Cation, right? Well, actually, no. All right? Because at the same time I attack you, you attack here. Because it's a transition state. As this starts pulling away, that starts developing partial positive. And you've got electrons. So I come away, but partial positive, so your electrons are going to go boom. And we have a three-membered ring. All this happens at the same time. This is your first intermediate. From here, the final step is to get there. Backside attack. Have we looked at it? Yes, it was the second one on the very important mechanism page. Another way to make carbon bond. This chloride, which has been sitting here, it didn't do anything. It comes in here and attacks here and kicks off the chlorine. This chlorine is going to be a leaving group. It leaves the carbon. All right, this was shown on that key mechanism page, the second example. And this is going to be backside. It's not important right now. When we start doing stereochemistry, this will be, okay? Now, when this bond's here, that gets kicked off, there's your product. That gives the product. You need to see how that is. Basically, this mechanism is known to involve a three-membered ring called a chloronium ion or a bromonium ion. These have actually been isolated and studied. It's hard to isolate them. We're okay. Let me show you this here. We could have attacked here and kicked the chlorine off of that. We're not doing that there. Why not attack this carbon and kick the chlorine off of that? Why attack this carbon and kick the chlorine off there? Because if we had done that, it would have been the same product as well. Here's the take-home. You attack the same place the carbocation would have been if it had been formed. It's not actually formed, but it's helpful. This is where you're going to ultimately attack. But you don't attack a free cation. You don't attack a free cation. You attack a carbon and kick off that back bonded halogen. when we look at stereochemistry on Monday, and you can look ahead, we've got stereochemistry here, because we know, we'll finish up here, if we attacked a free cation, which side would you attack from? Either side. Well, guess what? When you do this reaction, you don't get either side. You only get one side. So it makes no sense that it's a cation. The reason you only get one side is because you attack like this. And when you attack this way, it's only how? Our mechanism needs to match what we get in lab. Last thing, guys. I think we're okay. I need to make this point where we got it up here and do the last thing here. Some folks will talk about this. This three-membered ring, you can sort of strain. This thing back bonds. All right? But it is also very polar. I mean, that chlorine is pooling. You might ask, well, why did it even bond? We can talk about that. It's pooling. Is it going to pull more like this and leave that partial plus, or pull more like this? Well, which carbon can handle more positive? This one, because it has rich friends. It's the same as asking where you're going to make cation, left or right. Where are you going to have more partial plus? Here. And so that chlorine sees more partial plus there, and that's why it is attracted over there and bonds over there. Have a good weekend, guys. See some of you this afternoon upstairs. We'll get started exactly 2:30.